So this is day 2 of our wave lesson, and so we're looking at wave classifications. First, we're going to look at the general form. Now, you'll notice that these are not asterisk items. These are things that will be on quizzes, on exams. So you want to make sure that you're familiar with these things, especially if you're a junior and you're taking the exam. This is what's called a transverse wave. So transverse waves have a certain feature associated with them. Most of your math classes, because I'm sure you've been in a math class before or you've drawn some waves, most of the math classes draw things that look sort of transverse. The idea behind it is that the particles oscillate perpendicularly to the way the wave travels. I want to do some demonstrations here. I think it was yesterday, CJ, I was sending you some information via wave, correct? Okay. So I'm going to send a transverse wave your way, and I notice that the particles of the medium vibrate this way, whereas the wave travels that way. So we would say that the particles move perpendicularly to the way the wave travels. And again, you might look at, sometimes people are looking for memory aids. That T, you guys recognize that T sort of looks like a perpendicular set of lines? You might look at that and say, well, transverse T, perpendicular, that's the way the particles move in relation to the way the velocity is. Now, longitudinal waves are harder to draw. They're characterized by oftentimes compressions and expansions within the medium. And so the longitudinal wave, and I'll demonstrate that as well, the particles move in a parallel fashion in relation to the way the wave travels. I'm going to try to do that here by sending now CJ's way a longitudinal wave. So now what I'm doing is I'm trying to oscillate the particles parallel to the way the wave is traveling. Okay, so 2 main types of waves. Now, raise your hand. You've ever been in Lake Michigan before? What kind of waves are water waves? Are they transverse or are they longitudinal, would you say? Transverse. Do you guys agree they look sort of transverse? Yeah. Okay, so I want to show you one of the things I had you do yesterday was to pull up a interactive, and people did a nice job with that. We had 15 or 16 comments, and I appreciate that. So I want to show you the transverse versus longitudinal here with a simulation. So again, I showed these yesterday, but especially if you were gone, you might not understand these different waveforms. So we have the particles oscillating about their equilibrium positions through something called SHM, simple harmonic motion. We see the wave is traveling sort of in a straight line. This is a transverse wave. So the particles, again, are oscillating up and down, whereas the wave is traveling left to right. So let's take a look at a water wave for a moment. So for those of you that have ever been in Lake Michigan or in an ocean or something along those lines, you notice that the particles that make up the surface of the wave are neither vibrating transversely nor longitudinally. They're really a combination of them. So we would notice that it sort of looks like a circular kind of motion. If you've ridden on these waves, maybe you've done some body surfing or something along those lines, you often feel that you're pulled back away from shore as that water flows over you. And so it's really a combination of transverse and longitudinal. Now, usually we don't have the water actually moving from the outside lake into the shore until you get really close to the shore. So usually it's just the energy flowing. So the particles themselves are relatively stationary. You do notice that as you go underneath water, you try to ride underneath that wave, you still feel some of that oscillation, but it's just less of an amplitude. Okay? Raise your hand. You ever been in an earthquake? A couple people. I'm going to show you some Rayleigh surface waves, and so these are for earthquakes. And again, this is enrichment. You're not going to be asked to state anything about Rayleigh or surface waves related to this, but you can notice. What do you notice about this? What's different between the Rayleigh surface waves, which are often characterized in earthquakes? What's different between that kind of wave and the surface waves on water? Nick, what do you think?
Well,
thank you, by the way. Go ahead.
There's like 2 loops, and the top one is going left, and the
Yeah.
bottom one's going right.
It's a big difference. For one, some people notice that it's elliptical instead of circular, right? So the motion is still a combination of transverse and longitudinal, if you will. But a key difference between these is that we sort of change the direction of that motion. And so earthquakes are often, this is a shearing effect. So earthquakes will often create some shearing, which really causes damage to buildings. And the reason for that is because these particles, right along here, you can sort of see how those things are oscillating. Those things will sort of rip things apart because of those differences in direction. So it's interesting observation, thinking it. All right, so again, water waves, surface waves, and so forth. Okay, now the type of wave, there's mechanical waves that require a medium, and then there are non-mechanical waves that are usually just called electromagnetic waves. And so mechanical waves require a medium. Electromagnetic waves, things like light, do not require a medium. The restoring force is actually the E&M mutual induction. You might remember with the speaker activity that electricity can create magnetism, and magnetism can create electricity. Electromagnetic waves have their own restoring forces. The electric portion of a wave would generate its own magnetic portion, and so the magnetic portion sort of oscillates perpendicularly to the electric portion, and they create sort of a electromagnetic wave like sound. And so electromagnetic waves do not require a medium. Mechanical waves, sound is certainly mechanical wave. It needs a medium to travel through. Water, earthquake, ropes, this slinky, these are all mechanical. A medium is required to propagate that disturbance. Light waves do not need a medium. The one that's missing up here is the visible spectrum. So visible, you might recognize that as Roy G. Biv, very small portion of the electromagnetic spectrum. Some of you are going to be doing wave projects that involve light. So depending on what, some of you, anyone choose the X-ray maybe? Of your topic, X-ray? And do like the CAT scan? Okay, MRI? Okay, so you'll see that these are things that would sort of come into play for your particular project, if that's the one that you're doing, okay? So again, a lot of these things, you're just gonna see them as part of your project. Okay, now this is where I got to in my 4th hour. So my 4th hour is a little bit ahead of yours. So I wanna look now at these different waveforms. Based on 4th hour progress on this, a lot of people struggle with this portion. So I'm gonna go a little bit slower through this, make sure we have this stuff down. There's no asterisks on this. This means it's all part of the exam, right? So you gotta make sure you have these things down. Provide a name or symbol for each part of this wave. The wavelength, it's a Greek letter lambda. It's describing the length of a wave. So it's sometimes called the repeat distance. We see that a wave is continuous and it often repeats. So if I were to go from that portion on the wave to that portion on the wave and I measure that length, I get what's called the waveform. Now, the top of the wave, the maximum amplitude positive, is called the crest. So from a wave terminology standpoint, the crest of the wave is probably the wave that you surf. If you've done any surfing, you're sort of surfing just below the crest on the front side, right? Raise your hand, you've done any surfing? Is that true? You sort of surf on the shore side of the crest? At least if you're doing it correctly? Okay. Now, if that's called the crest, what's the maximum negative position called? The trough. So if you didn't know those terminologies, you're going to need to know that stuff. So just some vocabulary. What do we call the maximum displacement from equilibrium in our simpler harmonic motion stuff? What do we call that? Starts with an A, the amplitude. So again, wave names and wave features. You need to commit those to memory. Ooh, actually, you guys could, if you wanted to. You could be clever on your exam. Some of you guys are like you're thinking about the exam, especially if you're a junior. You are allowed an index card, both sides, 3x5. So if you're like I don't want to memorize vocabulary, you could throw some stuff down like that. Okay. Now I'm going to change this. Instead of it being a length measurement, I'm going to change this to a time measurement. So this is no longer a graph of displacement versus position. This is now displacement versus time. This would no longer be a wavelength. It'd be called a period. So now that would be a period value, the time between successive crests. Yesterday we did a little calculation. I think it was Noah that helped me. you determine the period of a tuning fork, 256 hertz. You had to take the reciprocal of that. If this time was from here to there, if that time was 0.001 seconds, that would equate to a frequency of 1 over that. And that would be about 1,000 hertz. For those that were gone yesterday, we talked about frequency being a cycles per second, period being a length of time. What's special about the 1,000 is that speaker, that when I had that thing set up, I was playing 1,000 hertz, 8-volt wave. So that tone that you're hearing was 1,000 hertz. Okay? Questions for me? I have a question for you. Raise your hand if you feel confident in drawing waveforms. Drawing waveforms. Okay. I was expecting a lot more people in my 4th hour to be able to do this, and they struggled with it. So I had to spend a decent amount of time on it. No problem. I'm going to do that with you here. This is not going to be homework because you're going to get this done in class today. So based on how things went 4th hour, I'm expecting that we'll spend a little bit of time on this. And then we got to look at the wave speed equations. That's the main topic for us. First, start by putting your name on this if you would. I am going to have you turn this in today just to make sure that you are keeping up with the material. What I would ask is that just give me your best effort. If you're confused on something, you can certainly talk to that person that you're sitting next to, see if you can help each other out. Important part of our class. If you are completely lost in the table, no one at the table knows how to do something, we will go over all of these things as well. Okay, so just take a moment, get your name on it. I want to do the first one with you. First one with you. All right. So guys, first thing, just make sure your name's on it. I want to go through and show you how to make some drawings here. And if you haven't been making these drawings in your math classes, it's okay. You'll probably do more waveform stuff if you go beyond Algebra 2. If you're only going up to Algebra 2, which is all that's required, you might not do a lot of wave things. In here, I got to do a little bit of mathematical review for you, and then we'll try to tie it into some physics-based stuff. We would call this just a standard wave. It's got a single crest, a single trough. It's got a full cycle. So this is one full wave. It's got a certain amplitude, and the amplitude is sort of bound between these two endpoints. If I call each block 1, so each one of these little blocks 1, could you tell me what is the amplitude of this wave? One, 2, 3, 4, 5. So we wouldn't say it's not peak to peak. The amplitude is the maximum displacement from equilibrium. This would be like an equilibrium position. So we would say the amplitude is 5. Now I'm just going to call the frequency 1, meaning that this completes one cycle in the amount of time. So we might say that the frequency is just 1. What I want to do is I want to draw a waveform that's twice as frequent and that has twice the amplitude. So in the same space, I want to draw now a wave that is twice the frequency and twice the amplitude. So first thing I'm going to do is I'm going to expand my boundaries. So instead of me being bound between 5 and -5, I'm going to be bound between 10 and -10. So I'm just going to put some lines here, 6, 7, 8, 9, 10. I'm just going to draw a new set of boundaries. And so 6, 7, 8, 9, 10. The waveform that I'm going to draw now is going to be bound between 10 and -10. Now I also want to draw twice the frequency. So that means instead of just completing one cycle, I want to complete 2 cycles in this time. So I'm going to identify some points along the graph that I'm going to go ahead and construct. The first one is going to be halfway between where this crest is and here. So I'm going to have this thing peak a little bit earlier. I'm going to go up to about this point, and I'm going to put a dot at that point to say it's got to peak earlier than this one because it's going to complete twice the waves in the same amount of time. So it's going to peak up to there, and then by the time this one gets to its maximum value, this one's going to be back at equilibrium. So it's twice as frequent. Now when I go to draw this first portion, we're just drawing a wave that looks like so. And I've got the first portion of that wave drawn. Now I'm going to go down to waves are repetitive in nature. So I'm going to go down and put another dot at that spot. And then another one up here to recognize that's what's going to be the next half of that wave. So again, I'd go through and draw that to look something like this. And I've got now a wave that shows twice the frequency with twice the amplitude. To complete that, I'm going to go ahead and draw the other half over here. Again, I identify some points along this wave to sort of help me construct that. Most waves can be divided into like 4 segments, right? We have a rising segment, a falling segment, something going to the negative, and then the other. So usually we'll just have some points that are located along there, about 4 or 5, to help me draw that graph. And so then I'd have a waveform that looks like this, goes down to here, and back up to there. Now this is very mathematical, and again, I know that math is not something that most of us love. If you've seen some math before, done some math, particularly things with unit circles, this will probably be review for you. Most kids my 4th hour, they did not see that. Twice the frequency, twice the amplitude. I might say that the amplitude of the new one has an amplitude of 10, and the frequency of 2. So it's twice as frequent with twice the amplitude. Now, I stopped 4th hour. I was like, all right, you guys go ahead and try this one. And hardly anyone was able to get it right off the bat. So I would like to show you this one as well. And then I'll have you try to do the other ones. This one's going to be half as frequent with half the amplitude. This one has an amplitude of 5. It's going to be half the amplitude. It's got to be about 2.5. So I'm just going to draw a set of boundaries in here to show the maximum positive. And it could show the maximum negative would be sort of bound between here. So again, that's just giving me some boundaries for that wave. I can get half the amplitude just by drawing it to go half as high as before. How do I get half the frequency? If that frequency is 1, then half of that would be 1/2. Instead of putting dots located here and here, and so I'm going to put very few dots on here. It's going to start at that point. It's going to reach its peak halfway in the middle, and then it's going to get back to the equilibrium position over there, and the waveform half as frequent with half the amplitude would look like that. Okay? Math people? Math people? The black line would be called y is equal to the sine of x. What would the one that we drew here be if you're a math person? The one that we drew. It wouldn't be y is equal to the sine of x. Yeah, go ahead.
That's parabola.
Not quite, thank you. This would be y is equal to 2 sine 2x. This would be y is equal to half sine half x. Okay, for those of you that are doing math stuff. Okay, with those, I'm going to give you a couple minutes. I want you guys to try to draw this one and that one. These down here caused a little bit more concern in my 4th hour, so I'm guessing that we're going to have the same struggles there. Take a couple minutes to see if you can get these things drawn. So twice the frequency, half the amplitude, half the frequency, twice the amplitude. Take a couple. Say it one more time. Yep, I'll show that to you one more time. Just a couple minutes, folks. Give it a shot. Okay, there, Chase.
Yeah, I was just gonna
Takes a lot of work to leave out the answer. It's a hobby.
What's your hobby there, Sam? Sam? Drawing waveforms?
Yeah.
Yes. Yeah, so if I'm in phase, so this is again mathematical speak here, not something a lot of people have a lot of experience with. These are, we would say that these are in phase with each other. They're both sort of going on at the same time. So we say it's okay. So we would normally start with them going up. Well, the amplitude, like this amplitude was given to me as 5.
Okay.
So this one.
Okay. Yes, yes.
Yep, you're welcome. If you're watching this from home, these guys are working on this drawing sheet. I do have this posted to the assignment page, and so if you are absent, you'd want to make sure you pick up one of these things here. Well, I'll be right with you. And so give yourself a chance to go at that and see what you can do with it. So this guy is actually looking at the so this drawing of these roots and this one is almost so again, I'm going to give you another one here. Well, so it's a little bit easier for you to sort of correct that unless you want to erase that. You're good? All right. It's all good. You're trying. That's all I can ask. Quick show of hands. How many people have those 2 drawings done? Okay. Another 20 seconds. I want to show you the top 2. The middle 2. The middle 2. The top 2 we did. All right. Just use the eHo pass, right? Okay. There they go. Let's go ahead and dry it. So this one, again, I'm going to end up having to have some dots located at some convenient places to help me draw this waveform. So if it's going to be half the amplitude and twice the frequency, that waveform would look something like this. And so that wave would look like so. Half the frequency, twice the frequency, half the amplitude. Now for this one over here, now I need it to be twice the amplitude and half the frequency, so I'm just going to put one single dot here. That's 5, 6, 7, 8, 9, 10. And that waveform almost looks like the waveform that I drew yesterday with you, dealing with the pendulum energy as a function of position. Okay. How do we do? Good. Bottom 2. I'm going to do one of these with you. I'm going to have you try the other one. Someone had asked me about what we mean by being in phase, and so I want to take a look at this one. I'm going to say this one is 90 degrees ahead in phase. A lot of kids struggle with this, 4th hour, so I'm going to sort of treat you like you haven't done anything with phase before. I'm going to identify this as a 0 degree portion of that wave. I'm going to identify the peak as the 90 degree portion of that wave, and this would be 180 degrees. This would be at 270, and this would be at 360. So this has to do with waveforms are repetitive in nature, and usually they'll go through something where there's like 4 portions of a wave, sort of like in a circle. And those of you that have been through a math class where you've done some unit circle business, those waves are very much related to these things here. So just like there's 360 degrees in a circle, there's usually 360 degrees in a waveform. Now, in your math classes, if you're gone beyond Algebra 2, you usually use pi halves radians, pi radians, and so forth. We're only going to worry about the degrees. Now, if I'm 90 degrees ahead, what I would do is I would draw a waveform that if this is at 0, I'm going to say that waveform is actually ahead of it by 90. So I'm going to have that one be at its peak at that particular point. So it's going to peak there. Instead of it peaking at that position, it's going to peak here. Now, just like this one sort of falls off at that point, so will this one. This one will go through a cycle that looks like so, and it's going to have the exact same frequency and same weight, same amplitude, but it's just going to be out of phase. All I'm going to do is identify some locations along here to show what that waveform would look like. And that waveform would be a same amplitude and same frequency. It's just different by 90 degrees of phase. For those of you that have done some math stuff, the black graph that's drawn there is y is equal to the sine of x. The one that I drew separately, the one that I drew that was 90 degrees ahead, do you know, Maddie, do you know what that one is called? No. This is the cosine. So the one that I drew is actually the cosine of x. They're only different by a shift. Okay? Now, this is not, you can put an asterisk by this. This is not a quiz question, an exam question. You don't have to worry about shifts this way. It's more of an extension. I'd like you to try this one. What if it were 90 degrees behind? So instead of it being ahead, like I showed here, what if it was 90 degrees behind? Take a moment, just see if you can do it. What would that graph look like? It's lagging by 90 degrees, not leading by 90. Take a moment, see if you can draw it. And for those that have tried it, again, it's not an exam or a quiz question that you have to worry about, but that's what that graph would look like. It'd be 90 degrees behind the original graph. It's sort of starting at 270, if you will. Okay? All right. Again, put an asterisk by that one. Now, guys, I'm going to give you credit for working on this. There's only going to be a few grades for seniors. I'm going to ask you, I'm going to have you give yourself a grade out of 5. You tried them. You have everything drawn on there. This is that accountability piece. Make sure your name's on it. Before you leave today, I'd ask that you get that turned in. Okay, so before you leave today. Any questions for me? All right, if you want to take a moment to get that turned in, you're welcome to now. And then heading back, we got to take a look at this next topic called wave velocity. Will, can I use you as another athletic example? Sure. All right, thank you. What's your? Do you run the 100 as well? Just 100 open. I know you're part of the group. You know what your split is? What's your split? Okay, throw that out. All right, so guys, we want to take a look at something. The last stuff that I looked at was very mathematical. Not a lot that would go on our physics stuff, but this one is much more of the physics connection. So I want to show you guys how wave speed depends on certain properties of that medium. Now, we got to go back to a little bit of stuff from our first unit, especially for those of you that are taking exams. That would be all juniors and perhaps some seniors. That is a fundamental equation from our first unit. Speed is just distance over time. Whether or not I use a V or an S, it's just talking about how fast something moves. Now, if I were to determine the speed at which this pulse wave travels, Maddie, you and I are 6 meters apart. If we put a tape measure out, you and I are 6 meters apart. I send a pulse down to Maddie, and I can time how long it takes for it to go from here to there. About how long does that take, would you say? If you had a stopwatch, just give me a number between like 1 second, 2 seconds, 3 seconds. About how long? Maddie, what would you say?
Like 6.
6 seconds?
4.
How about let's go with 3. Easier math. Okay, let's try this again. Are you ready? 1, 2, 3. 3 seconds to go 6 meters. Could you tell me how fast that pulse is moving? 2 what? 2 meters per second. Pretty simple calculation, right? 6 meters distant, it takes 3 seconds to travel, and we'd say its speed is about 3 meters per second. Now, if this were a continuous wave, not a pulse wave, it becomes harder to measure that because a continuous wave no longer looks to be moving. And I notice that all I see is something that looks like a waveform, but I don't see any motion other than this kind of motion. Would you guys agree? It's moving back and forth like this, but it doesn't appear to be moving between me and Maddie. So it does initially until it gets to that point. So we need to be able to calculate now its wave speed. I want to take, for example, Will's given me permission to talk about him as a runner. So Will, I was never a very fast runner. I tried, but I couldn't run really fast. I would say that if you're running, so Will's one of the 4x1 meter athletes that broke the school record recently, right? You guys are like 42 seconds, somewhere in that area? Okay. In order to run really fast, there's 2 main factors that a person that's a sprinter can control. One of those is what? Like if I want to go really fast, what's one of the things that I would like to be able to try to make as big as possible? Stride length. So the stride length is super important for runners. The longer you can make your stride, the more distance you can travel per step, right? Okay. Another thing that's super important for sprinters particularly is not just your stride. You know what else we might say is super important? It's okay if you don't know the term that we would use. It would be your cadence. What's your turnover rate? So when Will's running, and again, I'm glad I don't have this on video, but Will is moving, I would imagine, pretty fast cadence. Your feet are back and forth really quickly, and you have a really long stride, right? So if you have really long stride and really high cadence or turnover rate, you can run pretty fast. Usain Bolt, right? World record over for the 100 meters, like 9.59, something like that. Crazy, ridiculous. He would be out of the gates really slow. He'd fall behind in the front because he didn't have a lot of acceleration out of the block. But he had a huge top end speed. So by the end of that 10 meters, I mean, 100 meters, he's running super fast. But the 2 things that control your speed is essentially your cadence and your stride length. So what I want to do to develop this equation is I want to consider that a person walking behaves sort of like a wave. They have a stride length that's repetitive, and they have sort of a cadence, which is also repetitive. If I were to graph that person's position walking like it's a wave here, you would see something that looks like a waveform. When Will's in an all-out sprint, he's extending his stride length. That would look like a much longer, if you will, wave. The other thing that he controls is the cadence. He can really get his feet to cycle over really quickly. If I combine those 2 ideas, we can calculate this, get this equation for wave speed. We would say that the stride length is most similar to a wave's wavelength. So we're going to say that stride length is similar to wavelength. How far does his feet move per repetition? So stride length is like wavelength. The cadence, which is sort of like your turnover rate, actually, Shay, you're a long distance runner as well, right? Long distance runners have to have a certain cadence to be most efficient. It's about 180 steps per minute. That's similar to a frequency. So we can develop this equation for wave speed by considering how fast a person can run or walk based on their stride length and their frequency. Now I want to develop this equation for you. Speed is distance over time. When I'm talking about a wave, I'm going to use velocity instead of speed. I'm just going to use the term v. Instead of distance, I'm going to use a wavelength. So how far does his feet move per cycle? So I'm going to use a lambda to represent the distance. And instead of t, I'm going to talk about a very special time for Will's run, and that would be the period. So I just take wavelength divided by period. What we looked at yesterday when Noah helped me calculate the period for a 256 hertz tuning fork is that the period and the frequency are reciprocals. So I could take that period and replace it with that frequency by taking it from the denominator to the numerator. Now you don't have to derive the equation. The equation that you would have, and it's the only equation in your equation sheet, is that the wave velocity is simply frequency times wavelength. Instead of just writing that equation for you, I wanted you to see that it basically can be determined from speed as distance over time. Okay? Now, that's an equation you should have seen maybe in chemistry. Yes or no? In chemistry? Maddie, you've been in the full year of chemistry, right? Do you guys do stuff with that equation, velocity is frequency times wavelength? Do you remember that?
Yeah, we do some waves and stuff.
There is some stuff. That's okay. So you might have seen it before. You might not have. Regardless, it is something. There's no asterisk here, so it's something that you have to have down for this class. I want to show you a couple of things related to wave speed. So the factors that affect the speed of a wave. For Will, it's athletic ability. His stride length, his cadence, his turnover, all that has to do with his athletic ability. When I talk about wave speed, though, it doesn't have to do with the ability of anything. It has to do with the properties of the medium. So I'm looking at the medium affecting how fast that wave can travel. So in general, the speed of a wave depends on two things. What kind of wave is it? Is it a sound wave? Is it an earthquake? Is it a water wave? What kind of wave is it that's traveling? And what are the properties of the medium? So this is for mechanical waves. Mechanical waves require a medium. So what are the medium properties? Before I go through the things that affect it, can sound travel through air?
Yes.
Of course. Can it travel through water? Can it travel through liquid? Which does it travel more efficiently through, air or through water? In which medium does sound travel better, through air or through water? By far, it's water. And how you know that? You go out to the beach. You're playing in the water. You're above the water surface, and you're listening for boats. You can barely hear them. You go underwater. All of a sudden, you hear those boats that are 20 miles offshore. And why is that? Because the water is a much better medium for the sound to travel than air. It travels about 5 times faster in water than it does in air. Because the water is a different kind of medium for that sound than air is. How about between water and iron tracks for a railroad? What do you think travels more quickly? Sound through water or sound through like the metal tracks?
Solid.
Through the metal tracks of solid. The material properties greatly affect how fast the sound can travel. One is particle spacing. If the particles are really close together, the particles do not need to move very far to interact with the next particle. So if they're really close together, which they are in solids, it's going to travel a lot quicker than if they're far apart. How strong are the restoring forces? Solids, again, are characterized by really strong restoring forces, forces that hold things in really structured shapes. And then finally, the temperature affects the speed at which those particles can move. So temperature also affects these things. If speed is constant, then wavelength and frequency would be inversely related. Again, this is a mathematical connection that speed and or frequency and wavelength are inversely related if the speed is a constant. I'm going to write that out using some formula for a second. If the speed at which a wave travels depends on the material properties, then a certain frequency will produce a certain wavelength. If I make the frequency bigger, that should have the impact of making the wavelength smaller. If I make the frequency smaller, that should have the impact of making the wavelength bigger. Those two things are inversely related. To show you that, Maddie, I'm going to send you a relatively medium frequency wave. I get a sense of the wavelength. If I increase the frequency of my hand, you should notice the wavelength becomes smaller. And so a more frequent wave produces a shorter wavelength. If I make the frequency lower, what we'll notice is a much longer wavelength. The speed is dependent on the properties of the medium. To do that one more time, Ian, could you help me with this? Could you help me with this? I want to show you one more demonstration here. It's hard to do this discussion without seeing some things here. So, Ian, whatever you do, don't let go of that. Okay. Waves. Yeah, okay. Wave speed depends largely on material medium. Okay, so I'm sending you a little pulse wave. I notice that it goes down to you, reflects back. Well, how long does it take for it to go between Ian and I? About how long? In whole number of seconds. 1, 2, 3 seconds. Are you ready? Goes down and back. About how long? About 1 second? Okay. If he and I are 3 meters apart, that wave is traveling how fast? He's 3 meters away. It goes down and back in 1 second. What's the speed at which that pulse travels? 6 meters per second. There and back in 1 second. That's 6 meters, right? Okay. In, I want you to back up. Double the distance. Don't you let go. No, don't you let go. Keep going. Okay, you are now 6 meters away from me. I'm going to send a disturbance down to you. What will happen to the wave speed? Increase, decrease, or stay the same as it was before? Why? I made them further apart, but I changed the material properties. Would you agree that tension is stronger now than it was before? Yeah. And the tension is like an indication of the restoring force. The restoring force is much stronger. What that means is that the particles are going to vibrate more quickly back and forth. So when I send this out, it should take, you guys agree that it takes about a second to go there and back? Do you agree it's about a second? Well, you're twice as far away. What we did is we doubled that speed because we changed our tension. Now what I want to do is I want to show you the very first kind of waveform here. Now, don't let go of this. How much of a wave do you see at this particular point? Ian and I are 6 meters apart. What is the wavelength of this wave? If you can't see it, we're going to go up and down instead. So Ian and I are 6 meters apart. Don't you let go. What is the wavelength of this wave? It's not 6. It's not 1. Ian and I are 6 meters apart. 87. 12. Thank you. How did you get 12 for this, Shane?
I don't know.
Okay. So this is one. Would you guys agree this is 1/2 of a full wave? So 1/2 of a full wave is 6 meters. That means I would need 12 meters to occupy a full wave, right? Now what I'm going to do is I'm going to increase the frequency of my hand. As I increase the frequency of my hand, what I notice is that, you guys notice the wavelength got cut in half? You guys notice that? The same wave speed, but don't you let it go. The same wave speed, but now I've got twice the frequency and so half the wavelength. Okay, Ian, I'm gonna send along one that's even more aggressive with the frequency. Don't let it go. Okay, so I'm gonna try to get to, how much of a wave do you see right now? Can you say 1.5? Do you see why it's 1.5? There's a crest, there's a trough, there's a crest, but I have one crest, one trough, and one crest. You guys see that that's 1.5 full waves? The wavelength became even smaller. I'm going to try to increase the frequency more. The speed is dependent on the material properties. So I'm going to try to go sideways now. So as I increase that frequency of vibration, what I'm trying to get to here is a shorter wavelength. And you guys can see that that wavelength is shorter. How much of a wave do you see now? 2 full waves. It is vibrating very quickly. Last one in, don't let it go. Going to try to get 5 or 6 of those things in sort of a water wave kind of thing. So we're going to try it. So the idea behind this, you can get a waveform that looks like that, and I'm hoping that you don't let go of that. But can you guys see that waveform is sort of being created there with that wave speed? Okay. Ian, you may let that go. Thank you. All right, that's going to take us right up to the hour. Nice job with that. No homework today. What?